All right. Hey, folks. Hope you're having a great weekend. I got a couple of questions from some people of the homework this weekend, which was to finish the Desmos task that we started on Friday, where we had those two situations. One where it was linear because you were getting $1,000 every day, and the other one where you started with only one penny, but your pennies were doubling every day for 30 days for all the month of November. And then for another month into December, another 31 days, so 61 days total. So some people have asked me some questions about, hey, how do I use that equation, right? That equation to figure out an answer to this for day 61 or even at day 30, right? If I want to use the equation, how would I use that equation? The one that I showed you the other day. So I showed you this as the equation. It was y equals 0.01 times by 2 to the x power, 2 because it was doubling, and 0.01 because that's the starting number, or at least I thought that was the starting number here. Guys, I kind of screwed this one up here because check it out here. You had 1 cent on day one, okay, not day one. Why is that an issue here? Is 1 cent your starting number? No, 1 cent is not your starting number for the equation, at least, because this wouldn't be a y-intercept, right? X is 1 and y is 0.01. That's not a y-intercept. So this isn't a starting number. So your starting number here technically would be half of this, right? Because your money was doubling, right? Was doubling. You had 0.01. Then you had 0.02, right? You had 2 cents. And then you had twice as many cents as that. So you had 4 cents, right? 0.04. And then you had 8 cents. So the equation that I gave you was off a little bit here. Technically, the equation should have been this, and this is a little bit too complicated for where you're at right now. Technically, the equation is this. 0.005, a half of 1 cent. Wait, yeah, a half of 1 cent. Because if you doubled it, you would get to 1 cent on day one. Okay, so at day 0, you had half a cent. Let's say that, and the problem ended up working its way out from there. Okay, so let's ignore the equation for now. Let's quickly talk about this here, because I just want to show you that, hey, where did this come from? Where did this crazy equation come from, and why does this work? Like, what does this have to do with the fact that things are doubling, and where does that exponent come from? Well, really the key to understanding why this is the equation, why this equation just works, is thinking about what you did. How did you get that 2 cents? How did you get that 4 cents? How did you get that 8 cents? And think about the work that you did here. Okay, so what did you do? What did you do to get that 1 cent, for instance? Okay, that 1 cent is. Well, when the 1 cent, we started the problem, right? Let's put it here. Started the problem with 1 cent. Okay, that's the work that I did. It was given to us that we started with 1 cent here. Okay, and then what did you do to get 2 cents? Okay, where did you get 2 cents? Well, I did 0.01, as I'm guessing you did. And then what did you do to that to get 2 cents? Well, you multiplied it by 2, okay? 0.01 times by 2 equals 0.02, okay? Because this 0.01 multiplied by 2 just going to become 0.02. We're good to go. Okay, and then what did you do to get 0.04? Well, you took 0.04 and you multiplied it by 2 to get to 0.04. Or we can think about this as, well, what did you do to the original 1 cent, right? 1 cent. I was at 1 cent right now, and then I multiplied by 2, and then I multiplied by 2 again to get to 0.04. 0.01 times by 2 is 0.02, and 0.02 times by 2 is 0.04, and 0.04 times by times by 2 would be 0.08. So check it out here, guys. This is really what makes an exponential function. Exponential function is repeated multiplication, right? Repeated multiplication. So in linear functions, were you seeing repeated multiplication? No, you were seeing repeated addition or repeated subtraction. So you were using a constant rate of change. Here in an exponential pattern, it's growing through multiplication, right? A constant multiplier instead. 0.32 would be the next one, and so on and so forth, okay? So the reason why this is the equation that I thought it was earlier, it's actually this here, is because if we think of 0.01 as our starting number, we just keep multiplying it by 2 every single time we increase, okay? So we can think about this 0.04 as being 0.01 times by 2 gets us to 0.04. So check it out, 0.01 times by 2 is 0.02, times by 2 is 0.04. That's how we got to 0.04. 0.01 times by 2, times by 2, times by 2, that's how we got to 0.08. 0.1 times 2, okay? The next day, we times by 2. The next day, we times by 2. That's what got us to 0.08. Day 5, how many times have we multiplied by 2? 1, 2, 3, and 4. 0.01 times 2 is 0.02, times 2 is 0.04, times 2 is 0.08, times 2 is 0.16. I'm saying 0.0. That's the first one that's not 0.0. I got 0.16 here. All right. Next day, what do we have to do? How do we get to day 6? Well, we multiplied by 2 how many times? We multiplied by 2 5 times, right? Because there's be one more multiplication of 2. 1, 2, 3, 4, 5 gets us to 0.32, okay? How do we get to day 7? Right, day 7, 6 days have gone by since we had that original $1. So we've multiplied by 2 how many times? 1, 2, 3, 4, 5, 6 gets us to 0.64, okay? So guys, this is the closest thing that we have to thinking about what an equation for this particular scenario would be. So then the question is like, how would we generalize this into an equation? Because it's messy here to be like saying our equation, well, we started with 1 cent and then what happened? We tacked on all of these that we have to write out. Look how messy this is here. On day 8, we would have multiplied by 2 4 times, 5, 6, and 7. And that would have got us to $1.28. Finally, we have at least enough for like a cookie or something, $1.28. But it's really messy to show that out, showing the math out here. 0.1 times by 2 is 0.02. Times by 2 is 0.04. Times by 2 is 0.08. Times by 2 is 0.16. Times by 2 is 0.32. Times by 2 is 0.64. Times by 2 is 1.28, $1.28 right there. Okay, so this is messy. So that is why an equation like this would be messier here. So check it out, right? Repeated addition in math is multiplication. That's why slope, right? When we were doing linear functions, slope it showed through multiplication, like y equals 4x plus 2 means the y's would increase by 4 plus 4, even though it was 4 times x. So this is sort of similar here in exponential functions, and we don't have to worry about this right now. We'll study this a bit later here. But the reason why this is 2 to the x right here is because of the exact thing I just showed you in blue a second ago here. This here, and maybe I shouldn't have included the 0.01 in front. I shouldn't have. This is 2, 0.01 times by 2, times by 2, 2 times, 2, 3 times, 2, 4 times, 2, 5 times, 2, 6 times, and 2, 7 times. So what I have here is the amount of times we basically multiply plus 1, right? Plus 1. Too many times multiplying here. So anyways, this here is, right, an exponent, right? Because an exponent means repeated multiplication, okay? So think about that. 2 to the third power. 2 to the third power means multiply 2 times itself 3 times in a row, right? 2 to the third power equals 2 times 2 times 2. 2 to the fourth power equals 2 times 2 times 2 times 2, which equals, what, 16 at that point in time, right? So 2 to the fourth power. 2 to the fifth power is what? 2 to the fifth power is 2 times 2 times 2, 5 times in a row. So one more there, okay? That is 2 to the fifth power. Okay, exponent means repeated multiplication. So an exponent is shorthand, something called shorthand for repeated multiplication here. And that's why I showed you this as your equation for this here, because instead of doing this 8 times in a row right here, the ways I could get my answer right here, again, I'm just multiplying by 2 again and again and again, okay? So the way I could think about this and show this symbolically a little bit more cleanly here would be I could have that 0.01, but then I would multiply. Instead of writing all of these 2's like I have on top here, I can just write the 2 once, and I could take it to what power? Well, 1, 2, 3, 4, 5, 6, 7. That would be the 7th power right there. This would be the 8th power up top here. Okay, so this is how you can get any of your answers, right? Any of your answers right here. So what I know about this right here, $1.28, that came from the original 0.01, and then I had to multiply 2 7 times in a row because 7 days had gone by between day 1 and day 8. So 0.01 times 2 to the 8th power, that would get us to what our answer, we know our answer that for this row is going to be $2.56. But let me get my calculator up. I don't have my calculator up here. Let me get it up for you guys here. So I got this. I got 0.01. And the way you do this here, okay, so this is really the reason why you're asking here is like, how do I use this equation? The way you do something like this here, you got to follow your PEMDAS rules, right? Your order of operations, PEMDAS rules. So the question is here, do you do 0.01 times by 2 and then take that to the 8th power? No, that doesn't make sense because at PEMDAS, multiplication comes after exponent. So what you have to do here to get the answer is you got to do 2 to the 8th power first. So 2 to this y to the x to the y power means x to, you can specify what you want to take this to. So 2 to the 8th power is 256, and I'm going to multiply that by 0.01, and I got my answer. I got $2.56. So this equals $2.56, and that's how you use the equation. So this is 0.01 times by 2 to the 9th power, and I got 2 to the 9th power, and that's 512 times by 0.01, $5.12. Okay, so to answer your question, I know you who asked me this past weekend, to use this equation here, you take this, right? You do this 2 to the 9th power, right? You do this first, okay? And then you do the 0.1, you multiply second, okay? So do the exponent first, multiply second, because again, in the PEMDAS order of operations of evaluating something or simplifying something, that exponent is the second thing you do after you do parentheses, and there's nothing to simplify in parentheses here. So exponent and then multiplication is the third thing you do here. So you'd have to do exponent first and then multiplication afterwards. Hopefully that makes sense here. Okay, so wrapping this up here, just to show you that I think you should have got like $5 million or something like this, but just to show that your table should hopefully match up the equation. And you should have done this one here, or you could have done this as your equation. This is really complicated here. A valid equation would also have been this, 0.01 times by 2 to the, well, this is 2 to the 9th power, and that's when x is 10. This is 2 to the 8th power, and that's when x is 9. So this would have been to the x minus 1 power. Okay, that's pretty confusing right there. It's pretty advanced right there. So exponents can have little operations like that here. So 0.01 times 2 to the x minus 1 power, that technically is the correct equation, right? Correct equation, not the one that I showed you guys on Friday. That one was incorrect because, again, our starting number isn't 0.01 because that was day 1, not day 0. Remember, your starting number means what do you start at the beginning of the situation before it really even starts yet. Well, that's day 0. Day 1, you got a penny, so that means on day 0 you must have half that, right? Because if you're going times 2 this direction, you're going by divided by 2, going back up. Anyways, let's just get this answer down so you can check your answers. Question for how much money on day 30 and how much money on day 61. Let's do this in blue so we can see it nice and clearly. So this is going to be the amount of money. Let y equal be the amount of money in dollars, and x be the number of days. Okay, so what I'm going to do is day 30 isn't x. So let me do the number of days of. I can do x minus 1 in the exponent. So what I'm going to do here is 0.01, right? We started with 1 cent, and then what did we do to it each day? We multiplied 1 cent by 2. And in day 30, we started with 1 cent on day 1, so day 30 is 29 days away. So we would have multiplied 0.1 times 2. We would have done that 29 days in a row, okay? And that's the way we would have gotten day 30, November 30th, in our table. And I'm just going to show you, you're getting the same thing in the equation here. So let's check this one out. So remember, I got to do the exponent part first. Okay, so do this first. Okay, and then do that, multiply second. Okay, so I'm going to do 2 to the 29th power oops, 2 to the 29th power, and that's this big old number right here. And then I'm going to times by 0.01. And then I remember saying it would be like $5 million. And yes, look, there we go, about $5 million right here. Okay, so my answer to this one is here 5,368,709.12. Game's a chance, man. Literally, like if you went a whole month in a row guessing heads or tails, and you got a whole month in a row, and you started by betting a penny, you just doubled your money each time, you get over $5 million by the end. That's crazy. And craziness is that's a strange world we live in. But anyways, yeah, don't gamble. It's bad. All right, cool. Let's check this out here. How much money on day 61? Let's check this one out. We can get this day 61. So how many days have gone by since day one? 60 days have gone by. So that's just all you got to do. 0.01 times by 2 to the 60th power. And what we're going to get is this. 2 to the 60th power is that big old number. And then we're going to times by 0.01. And we're going to get this. Whoa, we got something in scientific notation because it's just so much money. This is pretty messed up. This is pretty crazy here because I haven't taught you scientific notation already. So this is the little E button right here, a little E thing right here. You hopefully studied scientific notation a little bit before. This is a way that calculators show really, really big numbers, like huge sums of money or sums of people in the world, or I don't know, the huge numbers that scientifically how far away stars are, right? Scientific notation might show that many miles because it's so huge. This is a really big number. So scientific notation is a way of showing really, really big numbers or really, really tiny numbers. Sometimes like very, very microscopic things or like germs or different cells or have certain like sizes to them that are really, really, really tiny. So anyways, I'm going to show you what this means here real quick because it's definitely teachable. So the amount of money that you have right here is actually in scientific notation because it's so big. And we'll try to figure out exactly what this looks like here. You would have 1.15 times by 10. So the E thing means times by 10 to the whatever the next letter number is written power. Okay. So 1.15, I just like to round it 2 decimal places. 1.15 times by 10 to the 16th power. 16th power. That is a huge number. Okay. 10 to the 16th power means that there would be 16 zeros basically after this, or right, we'd have to move this decimal place. So let's do that real quick. So this is how you change from scientific notation to a regular number. So this is 1.15 times by 10 to the 16th. What I have to do to see what that's equal to, so let's try to see if we can get this number right here. What that's equal to is I got to move this 16 spaces. Okay, I got to move this 16 spaces because if you multiply something by 10, right? If I multiply 1.15 by 10, I'd have 11.5, right? 1.15, right? It's like having multiplying 1 by 10 will give you to 10. Multiplying by 1.15, which is a little bit bigger than 1, it's going to be a little bit bigger than 10. So like 11.5. That's multiplying it by 10 once. 10 to the second power, right, would be multiplying something by 100. Okay, so 1.15 would become 115. And then I'd have, that would be the second power, but it's not to the second power, it's to the 16th power. So multiply 10 by 10, 16 times total. So I'd go once, I'd go twice, I go 3 times, I go 4 times, I go 5 times, I go 16 times total. But I'm going to have 1.15 times 10 to the second power would get me to 115. And second power would give me 115. So I still have 14 more times I'd have to multiply by 10. So I'm putting 14 more zeros. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that is approximately how much money you have. Whoa, whoa. If only life were as simple as this. What is that here? This is thousands. This gets us to millions. This gets us to billions. This gets us to trillions. And that gets us above trillions. Is that just like, I don't even know what's above trillions? Quadrillions? Yeah, quadrillions, I guess. You'd have 11 quadrillion dollars, 11.5 quadrillion dollars. That's crazy. Let's see here. Thousands, millions, billions, trillions, quadrillions. Is that right? I don't have to look at that up afterwards. So you have approximately, I hope I did this right. Did I do the point? Did I multiply by 0.01? Maybe I didn't do that. Hold on one second. So 2, yeah, maybe I didn't. 2 to the 60th power. Oh yeah, and I did multiply by 0.01, huh? Okay, so this is a huge number. So you'd have approximately 11.5 quadrillion dollars, and I don't even think there's that much money in the world. I don't like. I really don't think there's because trillions is the biggest thing that I hear expressed by. If you look at the amount that all publicly traded companies are, all stock markets in the world. Fun fact I learned this past weekend: if you added up all the valuations of any company, and that's like how we measure a lot of how much the world is worth, I guess, like in terms of production. It's $95 trillion. $95 trillion. We add up all privately traded companies, sorry, publicly traded companies in the world. Apple's plus Google's plus Facebook's plus McDonald's plus Nike plus Starbucks. Like add them all up together and what they're all worth and what they're what somebody's willing to pay for. That's $95 trillion. 11.5 quadrillion is like several times bigger than that. So, anyways, context this problem doesn't really make sense. You're not going to ever flip a coin in a row, flip a coin in the air 61 times in a row and be able to guess every single time. It's just impossible. It's just not going to happen. Anyways, 11.5 quadrillion is what I get for that one. I want to look up to make sure that is correct because that's crazy. Anyways, thank you guys for watching. I will take care. And have a good rest of your Sunday.